We began last time with the study of the kinematics of rigid bodies, and we looked at rotation about a fixed axis. Today we go one step further by looking at general plane motion. General plane motion just means that we have translation and rotation going on at the same time for our rigid body. And there are two methods of doing this. We're not going to spend as much time on this first one, which is called absolute velocity analysis. Instead, we're going to focus more on the relative velocity analysis. We can illustrate both of those with an example problem here. This is a slider crank mechanism. And so as the crank AB rotates at a certain speed, it causes the slider, which has point C on it, to move back and forth. And BC is the connector. And so while AB is rotating about a fixed axis, BC is under general plane motion. It's rotating and translating at the same time. And of course the slider is only translating. So if we look at this with absolute velocity analysis, the procedure goes like this. First of all, we define a linear dimension, in this case we'll call it S, that defines the position of the point that we're looking at, in this case point C. We write an equation for that dimension S as a function of the angle theta. Now the angle theta, of course, is shown as 45 degrees right here, but it's varying, of course, by the omega that's given. So once we know that equation, write that equation, we can then find the velocity of point C, which is just the same as S dot, using the chain rule. Now, that doesn't sound too bad, but it can get pretty complicated. The more complex the mechanism is, the harder it is to write that equation and to do the derivative. And when you try to get to our next step, which is going to be finding the acceleration of that point, then finding S double dot can be even more of a challenge. So our other method, the relative velocity analysis, we use this relative velocity equation, which says that for any 2 points on a rigid body, we can write the velocity of one relative to the other. And so in this case, the velocity of B is equal to the velocity of A. In this next term, omega, the angular velocity vector product with the position vector B relative to A. So that second part of the equation is just the velocity due to rotation of point B about point A. Then we add the translation term to that, which of course is just the velocity of A. Well, in this case, the velocity of A is going to be 0. It's a fixed point. Omega AB is known, and so all we have to do is take that cross product, and we can solve directly for the velocity of B. Now that we know the velocity of B, we work our way from B to C using that same equation, in this case written with CB in the second point, BB in the first one. But in this case, there's a couple of unknowns. I don't know what omega BC is. I do know what velocity B is. I also know what the, or can write the position vector, position of C relative to B. But I also don't know what the velocity of C is. So there are two unknowns. Excuse me. However, a vector equation gives us two scalar equations, and so there are really only two unknowns. That is, there's the magnitude of omega BC. I know that it's going to be about the z-axis. Again, planar motion means all of our rotations have to be about the z-axis. And I also know, because of the geometry of this problem, that the slider is constrained to move only in the x direction, so I can set its y component to 0. So there are two scalar unknowns that I can solve with the two scalar equations that come out of this vector equation. Now, that might seem like there's more steps involved, but as we'll see, this is probably the easiest method to use. It's much more systematic than the absolute velocity analysis. Let's talk about the cross product for just a moment, or vector product. Remember that because it's planar motion, your position vectors will only have I and j as the unit vectors, because again, all motion is within the xy plane. That means that rotations are going to be about the z-axis, so they'll only have k as the unit vector in the equation for omega. So when you do omega across the position vector, the only two cross products you have to remember are that k cross I gives us j, and k cross j gives you minus I. You can remember that with the right-hand rule. Now let's compare the two methods a little bit. First of all, it can be really difficult to develop that equation that we talked about that relate the variables in the absolute velocity method. In our case of the slider crank, it was relatively straightforward, but it can get kind of messy. Also, it gets kind of messy when you have to take the derivatives, but with the relative velocity method, you're only doing cross products. There is no differentiation that's required. And you can really apply that relative velocity method to any mechanism, no matter how complex. You're still just working from point to point, solving for your unknown. So it's a much more systematic approach and easier to understand in that regard, I think. Now, one disadvantage is that we're only finding the velocity for a specific orientation. That is, for the example problem we looked at, only for theta equals 45 degrees. The absolute method does give you an equation that works for any orientation. But of course, once you do find use the relative velocity analysis, you can also set that up in a spreadsheet so that you can find it for the complete range of motion of a mechanism. So next time, we're just going to keep going on relative velocity analysis and do a few more examples with that.